So we continue with RLC circuits in this lecture. We'll look at more circuits and more configurations and learn different concepts related to second order circuits. So last time we saw this RLC circuit where the switch was opened at t equal to 0 so that the current source went out of the circuit, and we looked at how simply the RLC circuit without any energy source reacted or responded to an initial energy. Now let us do the other way around. So let us close or connect this switch to the RLC circuit so that I0 gets connected to the RLC at t equal to 0, and for t less than 0 let's assume that the current source was not connected to the RLC circuit. So we follow the three steps, t less than 0, t equal to 0 plus, and t greater than 0. So for t less than 0 there was no current source, and we assume that the circuit was in steady state. So the inductor was a short circuit, capacitor was an open circuit, no energy source, so everything is 0. The inductor current is 0, the capacitor voltage, which is V, is also 0. So at t equal to 0 plus these two quantities, capacitor voltage, inductor current, of course do not change when the switch closes, so they stay 0. Let us also find IC. We'll find an expression for IC also by the end of this discussion. So IC is, so let us look at this circuit. So the inductor current is 0, so at t equal to 0 plus, the inductor behaves as an open circuit. The capacitor voltage is 0, so it behaves as a short circuit, and there is a current source connected now. So the entire current I0 flows through the capacitor because it acts as a short circuit. So the capacitor current at t equal to 0 plus becomes I0. Now let us look at, before we look, so there's a, let us look at this Laplace transform just for a second. I think you will learn Laplace transforms in your mathematics course or a signals and systems course. This is just telling you, so this bottom equation is a definition of what is called as a Laplace transform. It converts time domain functions to functions in S, where S is called a complex frequency. This is a definition, and one can prove that if capital F of x of s is a Laplace transform of a function x of t, then the Laplace transform of dx dt turns out to be s times x of s minus x at 0, t equal to 0, and the second derivative turns out to be s squared x of s minus something something. Now I put this in blue because for our purposes, we are not going to worry about these so-called initial conditions. Now we are going to use this concept. We don't really need to understand Laplace transforms at this point. The book calls this the operator method. He doesn't talk about where the operator method comes from. So I'm just putting this one slide to tell you the operator method comes from Laplace transforms. So here is what we'll do. So we want to now solve this circuit for t greater than 0, and for that purpose we want to derive the differential equation for this circuit. So we are going to use this operator method, which is very useful when circuits get more complex, as we'll see in the next circuit, which is a little more complex than this one. So what we do is, without justification, we say, well, we'll apply Laplace transform to the inductor equation and the capacitor equation. So the inductor equation is VL di by dt. If we take Laplace transform, we'll get V of S, and the derivative of IL will become S times IL, as we just saw. And then we call this S times L as the complex impedance of the inductor, and so it is called ZL, and ZL is S times L. Similarly, for the capacitor, we say capital IC of S is equal to C times S of Vs, and we write this as V times something times I, that something, the complex impedance then is 1 over SC. Now we replace L and C with SL and 1 by SC as the impedances. Alright, so that is what is here. So we just same circuit, we'll just replace L and C with these. And now we don't have, so what we did here was, instead of a derivative or a differential, we got an algebraic equation. So we use these algebraic equations here so that we can write the KVL in this form, KCL. So we say, well, these can be treated as equivalent to resistances once we have the S. And then we get an algebraic equation, and we want to, for now I'm going to solve for the inductor current. So we want to write an equation for the inductor current, and we just saw that V is equal to SL times IL. So we substitute that here, and so we get SL by R IL plus SC SL. So all that is just substitution of V equal to SL IL here. Alright, so we get this, and then we kind of make a polynomial. So we'll get SLC S squared IL plus L by R SIL plus IL equal to I0. Having gotten this equation, which is an equation in IL with all the IL terms on the left hand side and the sources on the right hand side, we convert the equation back to time domain. So we replace S with d by dt, S squared with d2 by dt squared, and we get the differential equation back. Alright, so this is the so-called operator method. I'll summarize this in just a minute. Okay, so here is the summary of the operation method. So the way we do this is, we replace L with SL, C with 1 by SC, and then we solve the circuit with this IV relationship for the inductor and the capacitor instead of the differential or the derivatives. So the derivatives go away, and then once we solve the circuit with these, then we'll get a polynomial equation in S. The left hand side of this equation, by the way, is a characteristic polynomial, which we'll come back to in a minute. Once we get this equation, we replace S with d by dt, S squared with d2 by dt squared, and we get back the differential equation. So this simplifies tremendously the derivation of the differential equation for any circuit. Alright, so this is the differential equation we get, and now let us solve this equation. So this differential equation is a second order equation because it has a second order term. It is non-homogeneous because the right hand side is not 0, and so this requires a different kind of solution, and it has constant coefficients as we have. So this left hand side we've seen before. Now again, as you study in mathematics, a non-homogeneous differential equation can be solved by using this form of solution where the complete solution of this differential equation is written as the sum of two parts. One part is the solution of the homogeneous equation, so ILN. So, and this homogeneous equation is often called the natural response of the circuit. Natural because this was solved with no source connected to the circuit. So this is how any circuit responds naturally when there is some initial energy supplied to that circuit. Plus what is called as a forced response, which is any solution of this differential equation. Alright, so what we are saying is the solution of this differential equation can be written as a sum of the solution of the homogeneous equation plus any solution of this equation. Now this is important because the general solution of any differential equation is always more than any solution. All right. So if I write only the one solution of this differential equation, then that will not give me the complete picture of how a current or voltage varies in a circuit, or for that matter any quantity or that satisfies this differential equation. Of course, second order differential equations are extremely common in a large number of natural systems, as you must have seen in the mathematics course, or you will see this semester, I think. Okay, so this we solved last time. We solved this differential equation with the right hand side equal to 0. So that we already did, and we found that the solution was of this form if the roots of the quadratic were real. So let's for now assume that the roots are real. Then ILN t can be written as a1 e raised to s1 t plus b1 e raised to s2 t. Okay, so that is a natural. Now let's think about the forced response, the ILF of t. Now it turns out that for linear systems and therefore linear circuits, the form of the forced response, the form of ILF t, will be the same as the form of the forcing function. The forcing function is the source, the independent source we've applied. So in our case, I0 is called the forcing function. So the form of the forced response will be the same as the form of I0. So for example, if I0 is DC, ILF will be DC. If I0 is sinusoidal, ILF will be sinusoidal. If I0 is exponential, ILF will be exponential. This is a property of linear circuits. If linear circuits are not linear, this will not be true. Our circuit is linear because our differential equation is linear, as we have seen before. Alright, so given that our forcing function, or I0, is DC, we can say that one solution of this differential equation will be DC. So we say, well, what is that DC? Well, let us try ILF equal to I0, which is a constant. All right. So if we put ILF equal to I0 in this differential equation, then DIL dt of course is 0 because I0 is a constant. So this is 0. Then of course the second derivative is 0, and therefore ILF equal to I0 does satisfy this differential equation, and therefore it is one possible solution, and that is enough for ILF of t. As I said, ILF of t can be anything that satisfies this differential equation. It doesn't matter what, but this is the simplest, so we use the simplest. And therefore we get the complete solution of IL of t as the IL natural plus IL of f, which comes out to be a1 e raised to s1 t plus b1 e raised to s2 t plus I0, which is the IL of t. Okay, so now we've got the form of the solution. Now we must find the constants a1 and b1. Now it is extremely important to remember that a1 and b1, or the constants of this solution, must be found only after writing the complete solution. Often what we forget and what we do is, so let me go back, we apply the initial conditions to this, only the natural solution. Alright, and then it will come out with all wrong answers. Alright, so be careful and remember that the initial conditions must be applied to the complete solution, because this is the IL, and we are saying this IL is whatever it is at t equal to 0, and its derivative is whatever it is at t equal to 0. The natural solution is only part of the solution. Alright, so let us apply initial condition. So we say IL at t equal to 0 plus is 0, because as we saw there was no source in the circuit for t less than 0, the current was 0, so that is equal to A1 plus B1 plus I0. And then di dt is V by L, and V is 0, so we get A1 S1 plus B1 S2, I'm sorry, this is B1 S2 equal to 0. So you can solve for A1 and B1, and it's easy, so I'm not solving. So we'll get the answer as IL of t equal to I0 by S1 minus S2 into S2 e raised to S1t minus S1 e raised to S2t plus I0. The I0 is there. So this is A1 and this is B1. Alright, so we found the solution for ILT. I am actually leaving it to you to find ICT and VT. V is straightforward, it is LdILdt, so you can just differentiate this and find V and find IC also. Alright, so please do that as homework. Also, plot IL of t if these values are given. Alright, so RLC and I0 are given. So you substitute these here and make a plot of IL, because as I had said earlier, it is important to learn to plot these functions, these expressions. Alright, now let's go to the next circuit, which is slightly more complex because there are two resistors. And so as you can imagine, the differential equation here will be a little more difficult to derive, and so we'll use the operator method and kind of illustrate the operator method to see how easily we can derive the differential equation. This also has a voltage source which has a unit step function. Now I actually forgot to talk about the unit step function before, and I also realized that one of the homework problems had this unit step function. So presumably you already know what the unit step function is, but anyway I'll do quickly definition of the unit step function. The unit step function u of t is defined as this. It is 0 for t less than 0 and it is 1 for t greater than 0. Okay, that is a definition of u of t. Note that u of t is not defined at t equal to 0, because at t equal to 0 it is making a transition abruptly from 0 to 1. So somebody asks the question, what is the value of u of t at t equal to 0? The answer is it is not defined. Now once u of t is defined, we can define auxiliary function. So u of t minus t0 will be a function which, so here the transition occurs at t equal to 0. So here the transition will occur when t minus t0 is equal to 0, which is t equal to t0. So this is the function u of t minus t0. It makes the transition at t equal to t0. Of course, t0 can be positive or negative. This is u of minus t. So u of minus t is 1 for t less than 0 and 0 for t greater than 0. Alright, so now let us solve our circuit. So we go through the three steps. So our function, let's go back, so is 0 for t less than 0 and 40 volts for t greater than 0. So for t less than 0, there is no voltage source in the circuit, no source of energy, everything will be 0. So IL is 0, V is 0. The capacitor voltage is V, IL is the inductor current. At t equal to 0 plus, the inductor current is 0, so it acts as an open circuit. The capacitor voltage is 0, so it acts as a short circuit. The voltage source is now connected. Well, the voltage source value is 40 volts now. So we are asked to find V, so let's find dV dt, because that's what we'll need for finding the constants in the final solution. So dV dt is IC by C, and IC is 0. Why is IC 0? Because this is an open circuit and so the 40 volts does not reach the capacitor. So the capacitor current is 0. Note that in this circuit, the entire 40 volts falls across the inductor at t equal to 0 plus. And the voltage across the capacitor of course is 0, the current is also 0. Okay. For step 3, we want to now derive the differential equation for this circuit. So we use the operator method. So we replace L with SL, C with 1 by SC, which is the complex impedance. And then we treat this as an algebraic circuit. So we write a KCL at the node V So we say V minus V0 divided by, so these two are in series now. So we say R1 plus SL, V minus V0 by R1 plus SL, V by R2 plus V by 1 by SC, which is SCV, equal to 0. And so now so we simplify this. So we get this. And then we write it in this form where we have the S squared term with a coefficient, the S term with a coefficient, and a S raised to 0 term, V equal to V0 R2. Alright, so this is operator method. L by SL, C by 1 by SC, write whatever equations KCL, KVL we want to write. Eventually write the equation for whatever quantity we are interested in our case V, with a polynomial in S, and then convert back the S to S to d by dt and S squared to d2 by dt squared, and we get our differential equation. So here is our differential equation. There was an LCR2, L plus R1 R2C, and R1 plus R2. LCR2, L plus R1 R2C, R1 plus R2. So this is our differential equation now. Now again, the solution of V will have a homogeneous part and a particular solution. The particular solution, because V0 is a constant voltage, so we find the particular solution simply by writing V as a DC quantity. And if V is a DC quantity, then the dV dt d2 dt squared is 0. So we just solve this last two terms for V, and so we'll get Vp of t as R2 by R1 plus R2 into V0. That is a one solution, and therefore that is Vp. For the homogeneous, we write the characteristic equation which we've done before. We assume that V is equal to e raised to st, and then that becomes S squared times e raised to st, etc., etc. And this is a characteristic equation, which, as I had noted before, so let me go back. So this is the characteristic equation. All right. So the e raised to st serves multiple purposes. So we say the characteristic equation, we equate it to 0, find the roots of S, and now of course we put numbers because we are given numbers, and so we put, and then we have a quadratic in S, so we solve for S. So all this I am not going through, but you should go through. Practicing with these numbers is important because the numbers are awkward, 10 raised to minus 10 and minus 8 and all that. So we solve and we get two values for S, minus 4.9 times 10 raised to 6 and minus 13.1 times 10 raised to 6. And then we write the final solution. So V of t is A e raised to S1t plus B e raised to S2t plus Vp. So let me go back again. So in our circuit, R1 is equal to R2 is equal to 100 ohms. So this is 100 by 200. So this is V0 by 2. So that is V0 by 2. So this is the solution of the differential equation. Now we must find A and B. So we impose initial conditions. So V at t equal to 0 is 0. So that is A plus B plus V0 by 2. dV by dt is also 0, which is equal to S1A plus S2B. And from these two we can find A and B, and I have found. And so this becomes the final solution of the differential equation. So it is interesting that this solution is extremely similar to the solution of the previous circuit, and you think about what are the similarities between these two circuits, that the solutions have come out practically identical, although this is V and that was I. All right, again, please plot V of t. It is straightforward, but it is important to plot. All right, so that is this lecture. Next lecture, so here we had a constant voltage source. Next lecture, we'll apply a sinusoidal voltage source.